All right, so far most series we have dealt with have had positive terms. In the following sections, we will study a series that contains both positive and negative terms. The simplest such series is called an alternative series, whose terms alternate in signs. For example, if we list the first 5 terms of the series, or the summation of n equals 1 to infinity of -1 raised to the n power, we could rewrite this series as a summation of n equals 0 to infinity of factoring out a -1 raised to the n times the 1/2 to the n. All right, so our first term would be 1 minus 1/2 plus 1/4 minus 1/8 plus 1/16 minus ... So notice our terms alternate from positive to negative, positive to negative. Okay, this makes this an alternating, and then we have that 1/2 to the n, which makes it a geometric series. So this is an alternating geometric series where our r is -1/2. So an alternating series occurs in 2 ways. Either the odd terms are negative, or the even terms are negative, but you're alternating from positive to negative, positive, negative. You might start with negative, you might start with positive. For these types of series, we're going to do something called the alternating series test. Let a sub n be greater than 0, so a sub n is positive, and the alternating series of the summation n equals 1 to infinity of -1 to the n power times a sub n. So a sub n is when we factor out that -1, or we could have it the summation of n equals 1 to infinity of -1 to the n plus 1 power times a sub n. So this depending if we start with negative or start with a positive value. This series converges if the following 2 conditions are met. So we have to find 2 conditions to be true. The first condition is that the limit as n goes to infinity of a sub n must equal 0, and a sub n plus 1 must be less than a sub n for all n. Okay, so basically that means that the series a sub n is decreasing. So if the limit of a sub n equals 0 and the series decreases, then we have a convergent alternating series. So let's look at our first example here. We're going to determine that this series diverges or converges. So let's first identify our a sub n term. Our a sub n term is 1/n. Now, 1/n we know is the same as the function f of x equals 1/x. The derivative of that is -1/x squared. And so that is negative. The derivative is negative. So that tells us that this is a decreasing series. So it meets that second condition that is decreasing. Next, let's check the limit. So the limit as n goes to infinity of 1/n is equal to 0, because 1 over a fraction is 0. So it meets the second condition, the other condition. So therefore, we can conclude that the original series, the alternating series, summation of n equals 1 to infinity of -1 to the n plus 1 power times 1/n, converges by the alternating series test. Okay, and the next one, instead of writing your a sub n term, I've expanded it out. So you have to come up with the actual a sub n term. So we got to recognize the pattern that's going on. I could write that first term 1 as 1/1. Well, wait, that doesn't work. Maybe I could write it as 1/0 factorial, because 0 factorial is also 1. And then, so let's make, if we have that 1/1 factorial, let it be equal to 1. Then we have minus 1/1 factorial plus 1/2 factorial minus 1/3 factorial. So that's what we're looking at. So it looks like our series, our a sub n term, is going to be equal to 1/n factorial, where n starts at 0. And so let's figure out this is increasing or decreasing by carrying our n plus 1 with our n term, our a sub n and our a sub n plus 1 term. And we figure that a sub n plus 1 is less than our a sub n term. So it tells us it's decreasing because that's not one we can do a derivative with. And so it meets that requirement. So now we're going to find the limit as n goes to infinity of our 1 over n factorial. And that's equal to 0 because it's a fraction. And so we can conclude that this series converges by the alternating series test because it met the two requirements. It's decreasing and the limit equals 0. Okay, let's do one more. Let's determine the convergence and divergence of the summation of n equals 1 to infinity of negative 1 to the n plus 1 power times n plus 1 over n. All right, so our a sub n term in this case is going to be the n plus 1 over n. Notice our a sub n is just everything but the alternating part, that negative 1 to the n plus 1 power. Okay, here you can see what's happening in our series. It's alternating, or we notice our signs are alternating. If you need to prove that it's alternating, you do this. If not, if you can just see that negative 1 raised to power, it tells you it's alternating. Either one works. So I got our a sub n term. So we need to figure out if this is increasing or decreasing. I can look at, well, let's look at our terms that we have listed out. 2, 3/2, 4/3, 5/4, 6/5. Notice that those fractions are decreasing. So our a sub n plus 1 is less than or equal to our a sub n term. And now next we need to figure out the limit as n goes to infinity of n over n plus 1 over n. So let's break up that fraction, write that n over n, which is 1 plus 1 over n. And the limit of 1 is 1. The limit of 1 over n is 0. So our limit equals 1. Uh-oh. We didn't get 0. So the alternating series test fails. The second condition, this condition that the limit as n goes to infinity of a sub n must be 0, failed. So we say the alternate series test fails, but we can't conclude it diverges just from that information. That means we need to choose another test. Okay? Just because the two conditions have to be met to prove convergence, but doesn't prove divergence that if you fail one of the tests. So the alternating series test fails. So that means let's try another test. Let's try direct comparison. So let's do direct comparison. Let's compare that n plus 1 over n with 1 over n. Let's try that. So let b of sub n equal 1 over n. Okay, so if our b sub n is 1 over n, well, 1 over n, that's a harmonic series, and we know harmonic series are divergent, so we're comparing it to a divergent harmonic series. And our a sub n is n plus 1 over n, and remember, if I broke that up and break it down, that gives us 1 plus 1 over n. So let's figure out which is larger, 1 over n or 1 plus 1 over n. Well, that's pretty easy to figure out. So our a sub n is n plus 1 over n, which simplifies down to 1 plus 1 over n. So it's very easy to see this, that 1 over n is less than 1 plus 1 over n. Okay, so our divergent series is smaller than our given series. So we can conclude that this series diverges by direct comparison.